Hello, and welcome to my KaoticEngine overview devlog. I'm just going to jump right into it. We're going to hop into Kaotic just to show you what's up with that. Right now, objects are kind of stationary, but as you can see, the light source, which is invisible, can move around. We got specular lighting, diffuse lighting, and we got a camera that moves around. These are all infinite detail, by the way, and I'll get into why that is and how that is. So, the first thing Kaotic does is, well, first of all, we grab some libraries: C basic library, SDL, Opengl. Then we got my own libraries. Then we initialize some variables, blah blah blah. And then we start with SDL. So we initialize everything. So like audio, video, input, all sorts of stuff that SDL handles. So then we set the version to core 4.6. Core is just a word for the basic OpenGL libraries. Then we get the desktop display mode. That's where we get the resolution for it. In my case, it would be 1920 by 1080. And then this value is for multi-sampling. It's a kind of anti-aliasing. I'll explain it later. And then this is where we create the window. Kaotic is the name of the window, so this little data up here, that would be Kaotic. And then we get the resolution. Right now I'm just using the resolution of the actual game for everything. I mean, I can set my own display mode easily, but I'm using the desktop display mode for my own purposes. Then we capture the mouse. That way we can't see the mouse. Well, actually, that way the mouse doesn't. That basically means the mouse input is being read by the engine. Sorry about that. And then we got full screen, OpenGL. These are all ways to determine that it's OpenGL. And we create the context for rendering, I believe. Actually, I think that might be. I'll figure it out later. And then these are all for capturing the mouse and keeping it inside the window. These are all error checks to make sure everything's okay. Because if there's no window, there's no game. And if there's no OpenGL context, then all this stuff is necessary. Then we have the float values that we're going to put for the triangle. So the top of the triangle is this. This is the top of the triangle. This is the bottom left, and this is the bottom right. And then we put all of those into these are all. This is for compute shaders. This is some leftover code from that. These are the shader. I'll get into that later. And then here is where we do we put all the data into, so game window. This is where we put all the data into the shader. I mean the GPU. This is how we define like which point, like where. So this is the position in GPU memory. Same as this, and then that's the number of values, and that's the type of values. I don't remember what this is for, and this is for the size of each, I think, and then this is the offset. Basically just putting the data into the GPU so that it can read it and not explode. And then we define the game objects. So C doesn't really have classes, but it has typedefs, which is basically the same thing, except you can't do like functions on it, but who cares? I can just use general functions like this. See. Then I have so there's materials. The materials are the same in the shader. So we have a material right now. It's just Boolean saying, okay, this is this and that and whatnot. And then we have a color and position, an SDF, I'll explain that later, an ID, just to make sure, keep track of it. And then we have the Overlord, which, manages all the objects. So then we put all the objects into the Overlord. I just love saying that. It's so funny. And then we have the game loop. So with the game loop, we have a delta time. Those of you who don't know what delta time is, it measures the time between frames. So it's used for movement so that your movement stays the same no matter how many frames per second you have. So if your game starts cutting down to like 30 FPS, you're not going to move slower than someone who has 60 FPS. Because normally you'd move per frame, right? But with multiplying the movement speed by delta, it allows you to move at a set pace so that you're moving within world time and not, how many frames per second you have. So then we check each event. I use booleans to check whether the key is down or whether it's up. If the key is down, then we execute this code. If it's up, then we don't. And then we have this here. As you can see here, where is it? There it is. If it's not equal to 0, then do all this code. But in this case, it's 0. If we press escape, then it's 0, and that means everything shuts down. Then we have mouse. That gets the inputs from SDL and converts it into something that can be used for looking around and for moving in local space. So when I turn left and move forward, then I'm moving forward and not sideways. This is just to make sure that all this stuff is real time, so that so this is a moving light, and that's just to make sure everything works fine in real time. These are all ways to put stuff into the shader, and because I can't add stuff like you can in C++ in between these values, I have to use special sprintf. So these put all the object data into the shader. And then then this is all the general stuff, so resolution, the mouse movement, the maximum number of marches. I'll get into that later. And then we have the color of the light source, so there's only one light right now. And then we have rendering, and then we swap between frames. So basically what it's doing is rendering frames. It renders 2 frames at once, sort of. It's not quite like that, but basically. And then once the current frame is on the screen, then it'll cut to the next one. It's for performance reasons. It allows less frame skipping. And then when we go to render, it goes through the vertex shader. Nothing fancy here, just says, okay, this is where it is in screen space, okay. And then we get into the juicy stuff. So, first things first, we define the version. It's 4.6 core. We have color. That's the out vector. So the color that this pixel is going to be colored is color. Then we have some uniform variables. That's basically when you send this stuff. That's what uniforms are. And so color, light position, cam position. Then we have the max distance and the number of objects that it'll take. So right now, Kaotic only supports a certain number of game objects, so you can't just spawn game objects in real time. But There is a way to do that with complicated data types and all this fancy stuff, but basically it can only support 4 right now. And that's it. So, same stuff, material, simplex, you saw all that. This variable means that, so if it's 0, then, we're going to grab the material of the computed object, and if it's 1, then it'll no longer grab that for the next Raymarch. Basically, so that, let me just show you. So let's say, where is it? Let's say we don't do this. Okay. Do you see those shadows and how they're purple? How we got like red shadows and everything's shadows has the same color as it? That's not supposed to happen. See, the way it works is that when you Raymarch from a shadow, it'll also color the shadow the color of the Raymarch because it's Raymarching to the thing, and that's not what I want to happen. So I have a boolean to stop it from happening. See, if scene equals 0, then we do the color. So first we get the resolution. We do this little math thing to make sure all the proportions are out on right. Then we have the ray origin. So, oh, I didn't mention the pipeline. So, I'll go to my render first, and then I'll explain how all this relates to the overall sphere of game development later. So, basically, the ray origin, I'll show it to you right here. So that little point right there, when we Raymarch, we want it in this way, and that's the origin. So we then do the ray direction. So we take the pixel position and we offset it by this math, and then we shoot it in a direction so that it can Raymarch for that pixel and do it accurately. Then we have this rotation matrix, and we change the ray direction based on where the mouse is and all that. And then we go in Raymarch. So we go up here to the Raymarch, and here we do, so we take the distance, so the distance is this value. Then we want to march in that distance, so we take that, we move this distance to that distance, and then we measure the smallest distance. Then we so depending on the SDF of the object, so we'll give it an object scene distance. For basically this says all of the objects, so iterate through all the objects, and then once you find an object, then you give the function, the SDF function, the object at that position, and then you subtract the position of the object from the point, and then you determine that point. So that second point is where the object itself is, and we made a vector of that from the from the position we're at. So then we determine which SDF it is from the object. That's why we need the object. And if it's 0, then we do the floor. If it's 1, the sphere, and so on. And then based on that, we take the distance and we go, okay, so if it's that, then we return that. We calculate the signed distance function at that point in space, basically. And then we go, okay, so if this is the smallest value, then we do this. If this is the smallest value, then we do this, stuff like that. And then once we reach the smallest value, then it returns that. So we check for all the smallest values, and if it's smaller than that, then okay. And then once we are done with all the objects, and we've got the smallest one out of all of them, then we return that small value. And then we do that again and again and again until either we reach the maximum number of marches, we exceed the maximum distance, or exceed the smallest distance. So, okay, then we check for, whether it's distance, and then then we do the SDF to make sure that, the smallest distance is, so basically if this is equal to the smallest, SDF so we're basically, when we reach here, we cast another sphere and make sure that it's that one. Because if we don't do that, then we end up with this. Just letting you just watch this. This will blow your mind. Oh, yeah, I forgot that. Delete that too. So then we do this. And everything is the same color. Reason being is it'll just grab the last object that this goes through. So in our case, the last object is purple. So we got to make sure that it's the object that we have Raymarched to, and then we return the distance after all that. So then we get the distance, and we give it to the lighting function and the ray origin. Then we get the normal vector of that so that we can calculate the some lighting stuff. So this is the Lambert shading for diffuse lighting. So there's two different kinds of lighting. There's diffuse and then specular. Specular is the shiny stuff, and diffuse is the I guess rougher stuff, softer stuff. And this is for diffuse lighting. This is just basically Lambert. It's very simple and not entirely realistic, but it does the job. Then we have the camera vector, so the distance from the camera to the fragment position. And then we determine the halfway vector for the specular lighting. We do this complicated equation. It's not quite as simple as Lambert, but it's more realistic. Then we do some colors and stuff. Diff color is the material color, all that. And then so if the distance exceeds the maximum distance, then we make sure to color it black. Otherwise, we get this. I'll show you that too. You see that stuff in the background? It's ugly, right? Yeah, so that's because once it Raymarches to a certain distance, it'll just... Look at that. Look at that. What is that? What is that? Can you explain to me what that is? But yeah, if it... otherwise, it'll just render that maximum distance, which is not what we want. We want it to not render that. So once it reaches the maximum distance, just get rid of it. Then we take that and we color the pixel with it, and that's how we do it. Okay, so you're probably wondering how Raymarching works. So for every let me just explain ray tracing first, because a lot of people are familiar with ray tracing but not Raymarching. Ray tracing is where you take a ray and you compare it to every object in the scene, and eventually you'll reach the distance. You can do that with triangles. A lot of people want to do that with triangles. You can do that with voxels. Dennis Gustafsson does that. I don't know if that's how you pronounce it. I don't know. He does that with voxels. In our case, we would do it with SDFs, but it's a lot less performant than Raymarching. and then you basically explode a bunch of different bunch of different rays in different directions. With path tracing, you do random directions and you just smack them together and hope it works. With ray tracing, you do a specific controlled amount of directions, and they are specific directions, usually in like a sphere shape. And that way we can get the right amount of them. It's not entirely accurate even then, but it's good enough. And then that counts for global illumination too. So that's how it works. With Raymarching, it's a bit different. Instead of comparing each ray to every object in the scene, or passing through different BVHs or anything, you march the distance. So that's what all that code was. So you take the smallest distance, and then you move the position to that, but in the direction of the ray, and then you do that again and again and again until you reach one of those 3 parameters. Then that's how it works. So here's how triangles are rendered with OpenGL, and this is how you normally render a scene, even in 2D. So what you do is you take 3 points, or if you're trying to do like a sprite, then you take 6, so another triangle. And the reason we use triangles is because they're the simplest geometric shape, so you can do a whole bunch of things with them. Basically, when the center of the pixel is inside the triangle, it'll render it. With anti-aliasing, however, you can sample. You can do different ways to do this, but basically you can make, if any part of the pixel is inside the triangle, then it is a certain color. Right, so like it's a certain amount of transparency. So I don't know exactly how it works, but that's basically the gist of it. If any part of it is touching the triangle, then it is colored in the same way as all the other pixels in the triangle, but with a little bit more transparency. That way the pixels aren't as like sharp in contrast to the other pixels, so you don't notice the aliasing as much. I think you might be able to notice it in Kaotic. Let me try. Actually, I don't think it works in the same way it does with Raymarching, but I'll figure something out with Raymarching. Probably SSAO or something like that. So anyway, I've explained what Kaotic does now, but how about when it in later? So what I'm working on right now is compute shaders. So I'm trying to get it so that I don't need the triangle at all. I can just do everything myself manually. And then Vulkan, I want to do Vulkan multi-pass rendering. So you render it once and then you just color the pixels different ways later. That way you can more easily debug stuff and all that sorts of stuff. And then I'd like an editor. An editor will change things a lot. Scripting as well. Actually, I might put that here. So with scripting and editor, that's what Unity does. That'll allow me to really make games. And then physics, that'll allow me to do collision detection, and then also like moving objects around and bouncing them off of each other. And I want a light array, so there's more than one light. Custom FDS, what I mean by that is like user-defined SDFs, so you could make your own SDFs. And then with the editor, there'd also be like adding SDFs together and doing stuff. Basically, Dreams for PS4, but a lot more advanced and a lot more complicated. I want to do animation, like linear interpolation, so we can do stuff like Blender or Unity, so you can like move characters around like you would expect. And I'll add some other stuff later, but right now that's the gist of it. Anyway, I want to see the bunny. So there's a bunny here. I've commented it out. Let me show you. Boop, boop. Boop, boop. So, let's compile that and then run it. If you observe, there is now a bunny. Now, of course, right now it tanks performance because I don't have any optimization set in place. Ooh. But yeah, bunny with infinite detail textures. Let me explain what the bunny exactly does, like how it works. It's a neural network generated thing. So what happened is someone developed a neural network that ray traces a mesh and then converts it into an SDF. So it'll take that and then multiply it by a bunch of these different matrices and add different parts of the distance into them, and then it'll do that. Also, this is a upside down bunny, as you could observe. That's because meshes don't always stay upright, so it's sideways. I think I could fix that by rotating it a bit. So that requires a matrix and all that fancy stuff. Well, I won't do that right now, but next devlog I will. But yeah, that's Kaotic, and I'll see you next time.